Hello and welcome to this webinar on the outlook for oil, natural gas and coal. This is one of a series of webinars that we are doing from the International Energy Agency on the new World Energy Outlook, which has been out for a few weeks now. Many thanks to all of you for joining us. We really appreciate that so many of you are taking the time to listen in. My name is Tim Gould and I'm one of the two heads of division that leads the World Energy Outlook team that produces the series of WEO publications each year. I'm going to be saying a few words of introduction, but the main voices you'll be hearing today are three senior colleagues from the World Energy Outlook team. That's Tae-Yoon Kim, Christophe Maglaid, and Johannes Truby. We are going to take a maximum of 1 hour of your time, and we're going to divide it roughly into two. So over the next 25 minutes, half an hour or so, we'll talk through some of the key findings from the new outlook relating to the fossil fuels. And then for the second half of our hour, we'll be very happy to hear your comments and take your questions. Some questions have already come in as when you registered, but we'd be very happy to receive more of them. You can use the browser for this webinar to submit questions as we go along. We look forward very much to hearing from you. What I'd like to do now is just to provide a little bit of context for our World Energy Outlook 2017, because in essence, we're talking about the intersection and interplay between four major upheavals that we are witnessing in today's global energy world. The first of these relates to the shale revolution in the United States. And just to emphasize that we've already seen some quite dramatic implications of this surge in shale oil and shale gas production, but we don't believe that that revolution is done. So we're in the middle of what is really an unparalleled expansion of oil and gas production within a single country, and that has a number of implications for trade flows, for energy security debate, and we'll come back to those a bit later on. A second unfinished revolution is relating to the deployment and costs of some key renewable technologies. We have included solar PV on the slide here, but you could make a similar observation about wind. You could make a similar observation in recent years about the cost of batteries. And that's upending some traditional assumptions about the way that we would meet our future energy needs. Thirdly, China. I think we're all used to watching China very closely when it comes to global trends, and that's been particularly true for coal and for oil. Our sense is that we would need to recalibrate some of those expectations when we think about the future. And certainly if you're looking at today's numbers for LNG imports to China, you'll see a very dramatic year-on-year increases for 2017 versus 2016. And China is also emerging as a leader in many clean energy technologies. And that's a product of this new era of China's economic development, which is underway. It's also the product of some quite significant policy changes. Today is the 8th of December, and earlier today, we launched in Beijing our China Energy Outlook, so a special focus in this year's World Energy Outlook on China. We'll make that the subject of a separate webinar in a few days' time, but certainly this is something that we consider to be a major factor affecting our global outlook. And finally, it's the growing importance of electricity in the energy system, in our lives. One aspect of that is related to increasing demand for cooling, say. Our overall energy demand outlook shows that growth is concentrated in countries that have quite temperate, warm climates. And that means as you see rising incomes in a place like India, so you get very strong new demand for electricity for cooling. Electric vehicles we'll come back to in a minute, but there's one, in a sense, broader shift that's underway, And that's this intersection between the digital economy and the energy economy. Some of the most profound implications of that are to be seen in the power sector. But there are also very strong implications for different areas of the oil and gas sector in particular, with companies increasingly looking to leverage the big data that they have, and also investigate some other areas like artificial intelligence for optimizing their upstream operations. In many ways, these four developments could be seen as positive for the outlook for affordable, sustainable energy. But certainly from an IEA perspective, they do require us to take a fresh look at certain core elements of our mandate related to energy security as well. And finally, we're well aware that there's many ways to look at the future of global energy. Today, we'll be focusing primarily on one of our scenarios for the future. It's called the New Policy Scenario, and it gives us a sense of where today's policy momentum is taking the energy sector, where today's technology trends are taking the energy sector. So it gives us a sense of the direction of travel. And that doesn't mean that this is where the IEA believes that we will end up in 2030 or 2040, in large part because governments have the chance to change direction in the meantime. And to help them in those deliberations, we also include another scenario. You'll be hearing about it towards the end of this presentation, and that's called the Sustainable Development Scenario. This describes where governments might wish to end up based on the objectives to which they have subscribed. And we take inspiration from for this scenario from the energy-related components of the United Nations Sustainable Development Agenda, and in particular, three key elements. One is Paris Climate Change Agreement, so finding a trajectory for energy-related CO2 emissions in particular that is consistent with the objectives of this agreement out to 2040. And a second element of that is a major reduction in the pollutants that cause poor air quality in many parts of the world. And thirdly, there is the aim to reach universal access to modern energy by 2030. So within that, we include not only electrification, but also clean cooking. And the clean cooking element has some quite strong implications for our discussion about the outlook for oil and gas. Oil because of the use of LPG in the residential sector, and likewise, gas can play a role in some aspects of the achievement of clean cooking. So with that, I'd like to pass the floor across to my colleague Tae-Yoon Kim to take us forward.
Thanks, Tim. A key subject in the global oil debate today is the advent of electric cars. We now have roughly 2 million electric cars on the road today, a tiny share of global conventional car fleet of around 1 billion. However, the momentum is clearly on the side of the electric vehicles. France and the UK announced the plan to ban conventional cars by 2040, and the Netherlands by 2030. In China, India also announced ambitious targets for electric vehicles. And there's a momentum from the company side too. Many big car companies are rolling out their long-term electric vehicle strategies. As a result, we expect strong growth for electric cars. By 2025, there are almost 50 million cars on the road, and this number reaches almost 300 million by 2040, a sizable share of the total car fleet of roughly 2 billion. What does this mean for oil market, especially for oil demand? We project oil demand for passenger cars peaks in the mid-2020s and then declines. 300 million electric cars displace around 2.5 million barrels per day of oil, and other alternative fuels like natural gas and biofuels save another 5 million barrels per day of oil. And there's an impact of improvement in vehicle fuel efficiency, which avoid around 12 million barrels per day of potential additional oil demand. So even with a doubling of the size of the global car fleet from 1 billion to 2 billion by 2040, we consume less oil in passenger cars than today. So having said that, many people talk about oil demand is going to peak and decline. We agree for passenger cars, and we also agree for other sectors such as buildings or power generation. But we don't agree for certain sectors such as trucks, aviation, and shipping, and most importantly, petrochemicals. The combined consequence is the global oil demand continued to grow from 94 million barrels per day today to 105 million barrels per day by 2040. Much stronger policy actions would be needed if we are to keep a lead on rising oil demand. For example, through widespread introduction of fuel efficiency policies for trucks or policies to improve the efficiency of material use. For example, petrochemicals are the largest source of oil demand growth over the coming 25 years. But the challenge here is that there are not many alternatives to displace oil consumption in the sector. With few options away from oil, we think improving the efficiency of material use can be an important strategy to reduce oil consumption in the sector. For example, by developing longer-lasting, lightweighting, and high-performance materials, or increasing recycling or reusing of plastic products. Today, on average, around 15% of plastics are collected for recycling. But if we double this rate, around 1.5 million barrels per day of oil, in other words, 10% of oil demand for petrochemicals, can be avoided globally, meaning that this is an area that requires more attention from policymakers. I talked some big changes on the demand side, but there are also big changes on the supply side. Some years ago, the trend line for US oil and gas was heading steadily downward. Then came what we called in the World Energy Outlook 2009 a silent revolution. First for shale gas and then for tight oil. This revolution is no longer silent. What we are seeing today is the rise in US oil and gas output that matches or exceeds all historical records. In the case of oil, the projected growth of tight oil matches the huge expansion in Saudi Arabia in 1960s and 70s. And in the case of natural gas, the projected growth exceeds the rise in Soviet gas production when the supergiant West Siberian field was developed. So it is unsurprising that when you have these two big developments at the same time, there's a big transformation that has major implications on the market within the US and but also globally. Within the US, major economic implications include the renaissance of energy-intensive industries such as petrochemicals. But the ripple effects are spreading across the globe as the US is transformed into a global exporter. This is already happening for gas, and more importantly, by the late 2020s, the US becomes a net oil exporter of oil. This is affecting our market outlooks, challenging incumbent suppliers, changing trade flows, and reshaping energy security risk. Let me talk about some more about changing trade flows. With increasing US output, together with output from Canada and Mexico, crude oil export from North America expanded by 4 million barrels per day over the projection period. Output from the Middle East also grows, but a large part of this is consumed within growing refineries in the region as well as outside the region, making less than 1 million barrels per day available for additional export. As a result, North America becomes the largest additional source of crude oil to the global market, ascending to the second largest crude oil exporter by 2040, ahead of Russia, Africa, South America, only behind the Middle East. I've said a few words about what this transformation in the US means, and a couple of points about what it does not mean. First, even though the US becomes a net oil exporter, it is still part of a deeply interconnected energy world. It still imports a large amount of crude oil to feed its refineries, just export lighter crude and refined product slightly more. So the health of US energy economy remains linked to what happens in neighbors in North America and in other parts of the world. Second, net oil export is not just a supply side story. It also depends on how oil demand evolves. US oil demand declines by more than 4 million barrels per day in our projection due to the improvement in fuel efficiency and the uptake of electric vehicles. Without the impact from this demand side, US would remain a net oil importer despite a remarkable growth of tight oil. Finally, the emergence of a new major exporter is certainly good news for oil importing countries such as those in Asia. However, as shown on the right side graph, Asia's crude oil import requirement expanded by a massive 9 million barrels per day, higher than the additional 4 MBD from North America and 1 MBD from the Middle East. This implies that they continue to rely on Middle Eastern oil and draw in all available crude oil from across the globe. So energy security concerns continue to be an important agenda for Asian importing countries. Now, my colleague Christophe will explain some of the issues around the cost evolution in upstream sector.
Since around about 2014, investment into new upstream projects has plummeted by around about 50%. But alongside this headline fall in investment has been around about a 40% reduction in the costs of developing new conventional projects, such as those in deep water areas. And today, a key question for the industry is whether these reductions that we've seen are a permanent change or whether they will simply reverse as we look into the future. To understand this, we first of all need to understand why costs fell in the first place. And for us, there are 4 key factors that explain reductions seen to date. First of all is the impact of technological improvements. We often hear when speaking to companies that there is a great level of potential and prospects for digital technologies to drive down the costs of developing new oil and gas fields. However, in our view, this is more of a factor for the future, which I'll come on to shortly. The cost reductions we've seen from technology improvements since 2014 are more through incremental improvements in drilling technology, such as the wider use of directional wells or elements such as inflow control devices. Secondly, alongside the drop in prices, companies have had lower levels of capital available and have also needed to ensure that the projects they do develop can remain competitive in the new price environment. And as a result, companies have placed much greater emphasis on developing only the highest value prospects. And this high grading of assets has led to an overall reduction in the average capital cost of projects that do go ahead. And this emphasis on executing only high value prospects had a further knock-on effect as the design of new projects that do go ahead have been re-evaluated. A number of proposed projects have been downsized by reducing the total level of oil that will be recovered or by lowering the planned level of peak production for that field. So, for example, the field in the United States, in the deep water, Mad Dog Phase 2, saw around about a 50% cost reduction, but this was partly achieved for a 10 to 20% reduction in the level of resources that will be produced from the field. But in our view, the most important factor in the overall drop in costs has been from the drop in unit costs. The demand for oil field labor and equipment has contracted sharply since 2014, and this dragged down the cost of these services and reduced the margins for service companies. And in parallel, the cost of many of the critical raw materials used for developing new oil and gas fields has also fallen. So of the 40% reduction in cost we've seen since 2014, we estimate that around about 2/3 of this is because of the drop in unit costs. What about the picture going forwards? Well, focusing first on future technology improvements, here it really is an increase in the use of digital technologies and digitalization that can have an important impact on reducing costs. For example, the use of in-well sensors to understand in real time what's happening below the surface can lead to faster decisions and increase the operating times of drilling rigs, wells, and facilities, and thereby reducing delays when executing new projects and therefore bringing down costs. We see progress on this front alongside the more traditional improvements such as we've seen in the past. These are clearly a structural reduction in costs, but the durability of the cost reductions from downsizing and simplification are much more difficult to assess. It's possible that they could represent structural changes in the types of projects developed, but this is likely only to be the case if there has been a lasting change in corporate behavior. So in the new policy scenario, we assume that there's a partial revision in the industry away from a rigid focus just on high-value projects, and this reverses some of the reductions that we've seen to date from downsizing and simplification. But there is some lasting change in corporate behavior that leads to more efficient and standardized processes and better and cheaper project designs. However, unit costs increase as prices increase out to 2025, and also the remaining conventional projects that need to be developed in the new policy scenario become more complex and less productive, and this reverses the improvements we've seen to date from asset high grading. And the net result is around about a 30% increase in the overall capital costs between 2016 and 2025, although we should still point out that despite this increase, the global average capital costs in 2025 remain around about 25% lower than 2014 levels. And with that, I'll hand it over to my colleague.
Thank you, Christoph. As those of you who are familiar with the World Energy Outlook certainly know, every year we have a different fuel focus in the book, and this year's fuel focus was on natural gas. We have a number of different scenarios in the World Energy Outlook that differ in many ways, but there's one thing that they all have in common, and that is that the contribution of natural gas to the global energy mix rises in all of them. For instance, demand for gas in the new policy scenario, main scenario, rises by 45% out to 2040. Gas is a relatively clean and flexible fuel that can help to achieve environmental goals as it displaces more polluting fuels. And that's something we've clearly seen last year in the United States, where we observed a major fuel switch from coal to gas in the power sector, and that has brought down CO2 emissions in the US. But gas markets are changing quite rapidly, and I'd like to use the opportunity here to run you through a number of important changes that we see happening over the next decades. The first one clearly is the rising role of trade, and especially the rising role of LNG. Today, most of the gas that is traded over long distance is traded via pipelines. These are the major flows between Europe and Russia, between Turkmenistan and China, for instance. But 90% of the growth in trade comes from LNG. And LNG is an inherently more flexible source than pipe gas, especially as rigidities like destination clauses and so on are gradually being removed. And with this in mind, the LNG or the global gas trade becomes more globalized and more interconnected over time. Now, where does all of this additional LNG come from? It comes over the short to medium term from the United States and Australia primarily, then also Russia, which is diversifying into LNG with its Yamal plant. And then you've certainly read in the news that Qatar has lifted its self-imposed moratorium. It leads to more LNG development as well. And then later, countries like Canada, East African countries like Mozambique and Tanzania are also joining the group of LNG exporters. And that's pointing to a greater level of diversification in the global gas trade, And that's potentially good news for customers, as that means that the intensity of competition is also growing. But then when we think of LNG importers, we typically think of advanced economies in the European Union, in Asia, like Korea or Japan. But in fact, almost all of the growth in LNG trade comes from developing countries in Asia. And here lie formidable opportunities for the global gas industry, for LNG exporters in particular. But here, that also means that there are a number of important challenges ahead. Long-term contracts have been key in underpinning investment in new gas infrastructure in the past, but lately, gas consumers have been less willing to enter long-term commitments. And this also comes at a time when oil price indexation, which is another LNG project finance classic, is gradually being abolished. Our projections indicate that from 2020 onwards, new investment decisions are needed in the LNG market. But it is, with these recent developments in mind, unclear to what degree these will be backed up with long-term contracts. The gas industry, therefore, needs to come up with new business models to secure financing of new projects. Then 80% of the increase in global gas demand over the next 25 years is set to come from developing countries. And from a sectoral perspective, it's perhaps surprising, but it's the industry that leads the demand growth in gas, not the power sector. And if we combine these two, that's also where another challenge lies. Factories and manufacturing plants, especially from the light industries, are typically geographically dispersed, and that means they need to have access to transmission and distribution infrastructure for them to grow gas demand. Now, many developing countries lack such transmission and distribution infrastructure. And for gas demand to grow in these places, policymakers there need to make a conscious decision to roll out such costly infrastructure. But obviously, policymakers would only do so if they're convinced that gas is a clean, reliable, and affordable fuel. And this brings me to the next challenge. Gas importers in developing countries have proven to be quite opportunistic buyers, quite price-sensitive buyers. And many of them have cheap coal within easy reach and often very good renewable energy potentials. And this implies that strict cost control for new LNG projects is absolutely paramount. In this context, it's certainly not surprising that both coal demand growth and coal import growth are concentrated in the price-sensitive areas of South and Southeast Asia. Countries in these regions experience strong energy demand growth in the coming decades, and they continue to use coal to complement a rapidly diversifying energy mix in our main scenario. Although coal generally remains a cheaper source of baseload generation than gas in many parts of Asia, the rapidly falling costs of renewables open a new front in the coal-dominated power systems. Solar PV becomes the cheapest source of new generation in India by 2025 and in China by 2030. The increases in coal imports that you see here in India and Southeast Asia are by and large offset by a drop in coal imports in Japan and Korea, the EU, and most importantly, China. And taking these ups and downs together, it results in a pretty flat trend line for coal trade out to 2040. As you can see here, we expect Chinese imports to decline by over 120 million tons of coal equivalent out to 2040. And with the 11% year-on-year import growth that we observed in China this year, it may seem counterintuitive, but we believe that Chinese coal demand has structurally peaked in 2013, and that the volatility in imports that we're seeing currently is largely a result of the government's efforts to restructure the domestic coal industry. And this has led to temporary tightness in the market and comparably high prices. And this in turn has, for the moment, reopened a window of arbitrage. In the longer term, though, coal demand is expected to move further inland in China as policymakers there prioritize economic development of the central and western provinces in China. And this, again, also improves the competitiveness of domestic coal in China. And with this, I hand back to my colleague, Christoph.
So far, we've been entirely discussing what happens under our central new policy scenario. But one question that's very pertinent for the fossil fuel industry at the minute is the role of natural gas and coal in a more environmentally benign energy system. Tim mentioned at the beginning that in this year's World Energy Outlook, we introduced the new Sustainable Development Scenario, which aims to provide an integrated approach to address all of the major energy-related UN Sustainable Development Goals. So just briefly again, these are achieving universal energy access by 2030, bringing about a substantial reduction in air pollutants, and achieving a near-term peak in CO2 emissions and a rapid decline thereafter. And in this scenario, the share of coal in the energy mix of all regions around the world falls out to 2040. However, the picture for gas is much more complex. And while we see gas grow at a global level, this masks some major differences that exist between different regions. So, for example, in regions such as the Middle East and in Russia, in which gas consumption is currently quite high and in which coal consumption is currently quite low, gas consumption in a sustainable development scenario falls over time. And this suggests that gas has relatively limited potential to help in the energy sector transition in these regions. Secondly, there's developing or emerging gas markets where coal consumption is currently quite high, and gas use in the sustainable development scenario rises over an extended period to 2040. Gas makes a sustained contribution towards decarbonizing the energy systems of these countries, as well as also reducing air pollution, particularly in the transport sector, and helping to achieve universal energy access in India, for example. Lying in between these two extremes, there are some regions, such as North America and in Europe, where we see gas consumption increasing for a certain period, but then after 2025, starting to decline. And this suggests that gas has the potential to make a larger contribution to the transition than it's doing currently in these regions, but this is only possible for a limited period. In these regions, there's a clear need to displace coal generation as quickly as is possible from the electricity mix. And during this period, while generation from renewable electricity does increase very rapidly, this is still not fast enough to offset entirely the loss of generation from coal power plants. And in these regions, which have a large level of unused or underused gas generation capacity, gas can clearly step into the breach that is left behind by the drop in coal. However, it's important to recognize that in these regions, the window of opportunity is very strictly time limited for natural gas. After 2025, as coal is increasingly already removed from the power system, and as we see an increasing carbon dioxide price in these regions, the tide turns against the use of gas-fired generation, away from providing baseload supply, and the utilization rates of combined cycle gas turbines in Europe and the United States falls. The role of gas in these regions therefore becomes much more support to integrating high levels of variable renewables. Another critical issue when considering gas and coal in the future energy mix is how the life cycle emissions intensity of the two fuels compare. And one frequent complaint that is made against natural gas is that the methane emissions along the value chain are so high that whenever these are taken into account, the life cycle emissions intensity of gas is actually worse than coal. And this was the main subject of one of our previous webinars, and I won't go into all the details now, but I just want to emphasize one of the key findings, since the life cycle intensity of coal and gas is a topic that keeps coming up. So we estimate that there are around about 42 million tons of methane that are emitted from the natural gas value chain globally. This includes emissions from the production of gas, the processing, the transport, whether that's by pipeline or by LNG, and a distribution to end-use consumers. There's also around about 40 million tons of methane emissions from coal production, which also shouldn't be forgotten. So what does this mean for the overall climate benefits of gas compared to coal? One other very important aspect to take into account when comparing the life cycle emissions intensity of the two fuels is how you can convert 1 ton of methane emitted to 1 ton of carbon dioxide. And for this conversion, it's common to rely upon the global warming potential of methane. Methane traps much more heat than carbon dioxide per unit of mass while it's in the atmosphere, but it stays there for a much shorter period of time. And unfortunately, this means that there's no simple conversion between a ton of methane and a ton of CO2. And most notably, the conversion factor that's used depends upon what time frame is being considered. So for example, if we consider the impact of methane over a 20-year time frame, 1 ton of methane is broadly equivalent to 85 tons of CO2, but over a 100-year time frame, a ton of methane is equal to around about 30 tons of CO2. Now this figure takes all of these factors into account: the methane and CO2 emissions from the production and consumption of gas and coal, whether we're interested in heat or electricity generated from the two fuels, and also the most recent global warming potential estimates given by the Intergovernmental Panel on Climate Change. So looking at this figure, if we're in the top right-hand corner in the brown area, then that suggests that coal is better than natural gas from a life cycle greenhouse gas perspective. And this is the case if you have a high level of methane leakage from natural gas, or if the conversion factor from methane to CO2 is high. If we're in the band in the middle, then natural gas is better than coal for electricity, but not for heat, because of the differences that exist in conversion efficiency between the two fuels. And if we're in the purple area, then gas is better than coal. So considering the intensity of the two fuels over a 100 time frame, that's the lighter blue bar, if the amount of gas that's leaked during its production and transport is below around about 5.5% of the gas that's produced, then gas will have a lower life cycle intensity than coal. Over a 20-year time frame, the leakage rate needs to be below 3% to be sure that gas is better than coal. So our estimate of 42 million tons of methane from the natural gas value chain broadly translates into an average leakage rate of around about 1.7%. And therefore, as a global average, gas is better than coal, regardless of the time frame under consideration. However, I want to finish with just 2 key caveats to this result. First of all, just because the global average is below the break-even point, it doesn't necessarily mean that all sources of gas from all countries are currently better than coal. Secondly, even if natural gas is always better than coal, simply comparing gas to the most emissions-intensive fuel is really setting the bar far too low, especially when we're considering the decarbonization efforts that are required under the Sustainable Development Scenario. If deep emissions reductions are to be realized, it's not sufficient just for gas to result in fewer greenhouse gas emissions than coal. The emission intensity of gas needs to fall to as low a level as is practicable. And with that, we're happy to take questions.
Thanks very much, Christoph. Thanks very much, Johannes and Tayun. I hope as we've gone through this presentation that we've actually already answered some of the questions that have come in. We had, for example, some questions about whether we cover the negative externalities of fossil fuel use in our work. Indeed, we look very closely at the energy-related CO2 emissions associated with fossil fuel combustion. But as Christoph's last slide made clear, we're also looking at other aspects of greenhouse gas emissions, so the methane leakage along the oil and gas value chain, and indeed in coal production as well. That certainly factors into the way that we look at the future of global energy. And likewise, we do couple our energy insights with some other global modeling efforts that allow us to talk also about the pollutants of some SOx and NOx and fine particulate matter. So those are the main contributors to poor air quality, both in urban environments around the world, but also the smoky indoor environments that you see in many developing countries due to the use of solid biomass as a cooking fuel. So, one other question that's come up, we need to make clear that gas is indeed cleaner than other fossil fuels, but not clean. And that's, I think, I hope we've addressed that question, but there's a chapter in the World Energy Outlook which in a sense, revisits the environmental case for gas and looks at the positive sides of that, so the positive sides in terms of combustion emissions, but also the potential things that raise questions about the climate benefits of gas on the methane side. So I hope that's clear enough. You're very welcome to send in additional questions now. We're very happy to answer them. I see them coming in. Just to clarify that we will be making the slides available on our website, and we will also making a recording available of this webinar as well. One first question that I wanted to put to colleagues here relates to investment, and naturally with a long-term outlook, we've talked a lot about some trends over the period to 2040. But what about some risks along the way? There's talk in many analytical publications about the risk of a supply crunch, perhaps not immediately visible, but say, somewhere on the horizon. Is that something that the IEA believes is a real risk for the medium or longer term outlook for markets? I think we're focusing here on oil and gas. So perhaps, let's take gas, Christoph, coal, oil.
So, as I mentioned also during the presentation, our modeling suggests that the overhang in the LNG market is largely absorbed in the first half of the 2020s, and with lag times for new projects in mind, that implies that very soon, around 2020, new investment decisions for projects, for LNG projects and other infrastructure projects are needed. Now, we've certainly also seen that gas prices have recently increased quite a lot in the Asia Pacific market. They're close to double digit again. Much of this has to do with delays in starting up new LNG facilities. So prices in 2018 might smoothen a little bit more, but it points to the clear possibility that the overhang in the LNG market could be absorbed much sooner than many observers think at the moment. And that stretches clearly into energy security territory, just because failure to bring new projects on in a timely manner could lead to tightness, could lead to price volatility. And this is exactly the problem here, because this jeopardizes potentially the perception of gas as a reliable and affordable fuel that is so important for many developing countries when they decide to grow their gas demand, when they decide to roll out infrastructure.
So on oil, I think it's important that we don't get too carried away with the rises that we've seen in tight oil. Tight oil from the United States has been incredibly impressive, the rates at which it has risen. And we've also seen in recent years production increasing from a number of regions such as Canada and Brazil because of investment decisions that were made prior to the drop in oil prices at the end of 2014. What we've seen since the drop in prices, however, is that the levels of exploration for new oil fields and a level of new oil fields receiving approval have dropped to historic lows. And while this won't have an impact necessarily upon the supply balance over the next few years, when we look out more towards the mid-2020s, over the medium term, there is a real risk that the shortfall in projects currently, and particularly in conventional projects, could have an impact upon reaching a smooth matching between supply and demand. We need to bear in mind that today, still around about 85% of oil production around the world comes from conventional sources. And so even though we have a large level of tight oil production growth, and while this can continue to help meet demand over the next few years, we shouldn't forget about the more traditional sources. And really, we do see there being a risk of the shortfall in investment into these traditional projects over the longer term, having an increasing impact upon the ability of markets to reach a smooth rebalancing.
Thanks, Christoph. I'm going to scroll back now to the slide that we had on costs because I have a question in from Sachin Shah relating to, we talked a lot about capital cost per barrel for conventional projects. What's the evolution for unconventional, i.e., light tight oil in the United States? Just to emphasize that the slide now on the screen, that is a relation to conventional oil projects. So we're asking to fill in the sort of indicative way the rest of the picture there.
So yeah, so these, as Tim said, this is just for conventional projects, and the reductions in costs that we've seen for unconventional projects, and I'm talking here about tight oil in the United States, have been even more impressive than these cost reductions. And these reductions haven't really just been because of drops in unit costs. We have seen real efficiency improvements and real improvements in the type of technology being used to access tight oil resources. So tight oil resources around the United States dropped even more than this 40% reduction since 2014. However, I should perhaps just note that since 2016, we've seen an increase in activity in the United States, and this has been carrying with it an increase in drilling that's been taking place, and as a result, costs have actually started to increase again slightly in tight oil areas. So I mean, that really just highlights the importance, I think, of being able to differentiate between structural reductions, such as technology improvements and improvements in efficiency, and more cyclical reductions, such as from drops in the cost of a drilling rig or in services.
Thanks very much, Christoph. Question now, which I think Sayun will pick up. There are new regulations on the fuels used for maritime transport coming in from 2020, relating to the sulfur content of these fuels. Can you talk through what the implications of that will be for product demand oil markets?
Yes, for the IMO things. So until 2020, I think this industry is likely to take a wait-and-see approaches because there's no incentives for early compliance. But around 2020, there could be big changes that could affect the refining industry and oil product markets. The shippers may initially opt for the low sulfur fuel oil as they prefer less capital-intensive options. But the supply of this low sulfur fuel oil is limited. So the next option would be to go for marine gas oil at the expense of usual high sulfur fuel oil. And this may lead to a major drop in high sulfur fuel oil prices, and which it happens will improve the economics of installing scrubbers. So we think over time, the number of scrubbers installed increase, and then it can make demand for high sulfur fuel oil gradually recover. So the implication to the refining industry is those who have low yield of high sulfur fuel oil and high yield of diesel stand to benefit from good margins around the 2020s. But on the contrary, the simpler refiners that produce a large portion of high sulfur fuel oil might suffer from these regulations. And one word about this LNG consumption in this maritime transport. So there's a growing interest about this consumption of LNG in shippings. LNG consumption grows rapidly from a negligible level to nearly 60 BCM by 2040, around 12% of maritime fuel consumption. But currently, the IMO regulation is just only on sulfur. So if it covers other emissions such as CO2, then I think there's a chance that LNG get more push.
Thanks very much, Sayun. And that last point on LNG, I hope that answers the question that came in from Amitav Kumar. This is a question from Mr. Wei, who was asking about, are there technologies out there that could reduce the environmental impact of coal, so the so-called clean coal debate? What about the use of CCUS, so carbon capture, utilization and storage in our scenarios? What role does that play?
Thanks, Tim. The role of clean coal technologies and the role of coal and power generation in general depends strongly on the scenario. For instance, in the new policy scenario, our main scenario, we see a significant slowdown in terms of coal additions. Over the last 15, 16 years, so since 2000, the year 2000, around 900 gigawatts of coal were added to the global coal fleet. but the net additions out to 2040 are only 400 gigawatts. So a significant slowdown in coal additions. But most of this is happening in developing Asia, and there we see a significant shift towards some more efficient technologies. So 3/4 of the new coal plants that are being built use ultra supercritical and supercritical technology with much higher efficiencies than the more traditional subcritical technologies. And at the same time, it is very important that the growth or the coal use in Asia's power systems is flanked with air pollution regulation to make sure that new plants built are forced to install modern control technology for air pollutants such as SO2, NOx, and particulate matter. And then the situation for coal-fired power generation is vastly different in our sustainable development scenario, where unabated coal use is not consistent with the assumptions of the scenario. And here we see a shift towards CCS, CCUS, where 200 or just over 200 gigawatts of coal plants use CCS technology. And here one country is absolutely paramount, and that's China, where we see 3/4 of the CCS development in the coal-fired sector happening over the next 25 years.
Thanks very much, Johannes. We had a couple of inquiries coming in about the role of hydrogen in our scenarios. Hydrogen is coming back into the energy debate as a possible solution to a number of issues, perhaps in relation to energy storage, in relation to long-term utilization of current natural gas infrastructure. There's also a question coming in from Ana Marquez Leandro about what about the use of hydrogen for freight transport and industry? What do we consider likely? To what extent is that factored into the scenarios, and what are the impacts on oil demand? So, Christoph.
So I think, first of all, we should recognize that hydrogen is already used to quite a large extent in the industry sector, but it's generally created there by steam reforming natural gas, or, for example, such as to manufacture ammonia and methanol in the refining sector. But if we're talking about hydrogen in some of the other sectors, we're probably more interested in the role of hydrogen in the low carbon energy sector transition. So clearly a fundamental aspect of this is that you have to use low carbon sources to produce that hydrogen for hydrogen to be useful. Now there's a variety of ways in which that can happen, and one of them which is often talked about is power to gas, where you use electricity, and in particular you could use electricity from intermittent sources such as wind or solar when there's an excess of electricity in the system to produce hydrogen. And we look at this in this year's World Energy Outlook, and broadly speaking, the potential for just using what would otherwise be curtailed electricity to produce hydrogen doesn't really seem to work particularly well for hydrogen. This is mainly because the capital investments that are required to convert electricity into hydrogen are very high, and you're not going to want to just use or run that bit of kit just using electricity from the system whenever the wind is blowing particularly hard or the sun is shining in particular. Really what's going to happen is you're going to have to use dedicated electricity facilities to produce this hydrogen. Or, for example, you could produce hydrogen by splitting the CO2, the carbon from the hydrogen atom, whenever you produce natural gas, capturing that CO2 somehow or using it elsewhere, and then using that hydrogen in the grid. And then another key question, as well as how you produce that hydrogen, is how you transport it to the end users. In existing natural gas pipelines, both on the transmission side and the distribution side, there is an ability to inject a certain amount of hydrogen into these pipes. However, that level of hydrogen you can inject isn't necessarily that high, simply because that can corrode the pipeline and can lead to failures. And so really, if you're talking about hydrogen playing a widespread role in the energy system, you need to have dedicated hydrogen infrastructure, such as pipelines, to transport that hydrogen from where it's produced to where it's consumed. And so we shouldn't just think of hydrogen just being transported in those ways, because that can be quite an expensive way to construct a dedicated hydrogen pipeline. We should also look at other ways in which you can use that hydrogen. For example, if you can transform that hydrogen into ammonia, you could use that ammonia in different parts of the energy system, and that's transporting and using hydrogen by proxy. We have a certain level of hydrogen coming through in our energy modeling in the sustainable development scenario. However, this level of hydrogen injection into pipelines, the use of hydrogen as a dedicated vector, and the use of hydrogen as a vector via ammonia is relatively small, simply because the experiences to date have been that this is quite an expensive thing, and we need to see much more cost reductions looking forward to have hydrogen as a central part of our sustainable development scenario.
Thanks very much, Christoph. We are almost out of time, but I'm going to direct one more question to Johannes, and that relates to natural gas, it relates to LNG, and it relates to the role of US LNG within the system. And this question that came in from Dokyun Lee. How does the competitiveness of US relate to other new sources or existing sources of LNG within the system? Is it towards the bottom of that supply curve for delivery into Europe or delivery into Asia? How does it compare to some of the other new sources of gas that you talked about in the slide?
Yeah, I think that's a very good, very important question. If we look at the competitiveness of US LNG, I think two things are important. The first one is the domestic US gas price, because that's what US LNG will be priced off. And the second one is whether we're looking at short-term marginal cost or whether we're looking at long-term marginal cost. For the first one, the US supply cost curve appears to be quite flat for a large amount of resources, and there are good reasons to believe that US gas prices are staying at relatively low levels for a while. Nevertheless, and that means that US exporters could, on a short-term marginal cost basis, be quite competitive suppliers into Europe and into Asia as well. But then that only works for a short period of time. And if you take full costs into account, then the US LNG would come into Europe and Asia at around about, say, $9 per MBTU in 2025. And that's based on a Henry Hub price assumption of $3.7 per MBTU. Now, that implies that US LNG shouldn't be seen as a strictly low cost source of gas. It comes in pretty much in the middle between lower cost suppliers like Russia and Qatar, and more high cost supply come second wave Australian, for instance, and a lot of domestic developments in various countries around the world.
Okay, thanks very much. I think our hour is up. Just to emphasize that, of course, this webinar was explicitly devoted to talking about oil, natural gas, and coal. But we're all aware that we've only been looking at one part of the energy system. We had another webinar, which is also soon to be up on our website, which looked explicitly at power, renewables, and efficiency, and some of the questions that have come in related to energy storage technologies or the way to handle high penetration of variable renewables. Those were covered in other webinars. We'll be replying to those questions that we didn't manage to cover so far with either a direction to other places where they've been answered, or the answers directly where they relate to the topics of today's webinar. And with that, it remains only to say thank you very much to colleagues who've been presenting today, to Dokyun, to Johannes, and to Christoph, and in particular, of course, to all of you who've shared the last hour with us. Many thanks.